Hello, analysis students. So, we've developed a lot of techniques for the study of sequences, and in particular the limits of sequences. We have things like the Cauchy criterion, which says that a sequence converges if and only if it's Cauchy. We have things like the monotone convergence theorem, which says that if a sequence is monotone and bounded, then that sequence converges. I would like to study a different thing you can do with sequences, which is instead of seeing what the sequence tends to when the index of the sequence is really, really big, let's see what happens when you try to add up all of the terms of a sequence. And you'll remember this being an important idea in places like Calculus 2. So let's start exploring these. In particular, things like these series we'll get to at close to the end of the semester when we study things like power series of functions. So let's go ahead and get started. If you have a sequence, AK, and when I'm talking about series, I'll usually index my sequences with the letter K instead of the letter N. It obviously doesn't matter. You can define a sequence of partial sums associated to that sequence by the rule that Sn is the sum of the first n terms of the sequence. Written in summation notation, that's the sum from k equals 1 to n of AK. And depending on the exact context, this k equals 1, sometimes we won't want our series to start at k equals 1. Sometimes we'll want it to start at k equals 0. Sometimes we'll want k equal to 10 to be the initial term. It obviously makes no difference to the theory where we decide to start our indexing value. I'll say that a series converges to some number L, and I'll write the sum from k equals 1 to infinity of AK is equal to L if, well, you kind of know what this should mean. This should mean something like the limit as n goes to infinity of the sum from k equals 1 to n of AK. That's what it should mean to add up all of the terms. I don't know how to add them all up at once, but I know how to add up finitely many terms. I can take the limit as n gets very big. So I'll say that the series converges to some number L and write the sum from k equals 1 to infinity of AK is equal to L if, well, I have a name for, this number. This is Sn. So I'll say that the limit of a series is equal to L if Sn converges to L. And notice, this thing right here is a sequence. That is the sequence of partial sums. Similarly, I will say that the series diverges if the sequence Sn diverges. I'll say that the series diverges to plus or minus infinity if, you guessed it, Sn diverges to, that's totally illegible, 2 plus or minus infinity. So all this definition says is if you want to say something about a series, if someone asks you to say something about something that looks like this, all they're asking you to do is say something about this sequence. So, as some warm-ups, let's prove some basic properties of series. So here's one. Let's suppose that AK and BK are sequences. Let's assume that the series, the sum of all of the AKs is A, the sum of all of the BKs is B, and C is a number. Then, well, let's try to decide what the sum of all of the AKs plus BKs is. So informally, that seems like, well, you should be able to, like, I don't know, if it were a finite sum, you could definitely just rearrange the order in which things were written and rewrite this as the sum off to the side. It sure seems like the sum of all of the AKs plus BKs should be the same thing as adding up all of the AKs and then adding up all of the BKs. And indeed, that's our first result. If the series associated with AK converges to A and the series of all of the BKs converges to B, then the sum of all of the AKs plus BKs is A plus B. Similarly, if you multiply every term of a series by c, you wind up with that same number times the sum of all of the AKs. And I'm only going to prove the first of these two results. This one is homework. So let's prove it. Let's prove the first of these two formulas. So let's let AK and BK be sequences. Let A and B be numbers. Let's assume that the sum of all of the AKs is A and the sum of all of the BKs is B. So that first line is just set up the givens. Now this is a statement about convergence of series. Convergence of series is just a thing about convergence of sequences of partial sums. So let's let Sn be the sequence of partial sums associated with AK. So that is Sn is equal to the sum from k equals 1 up to n of AK. Tn is the sum from k equals 1 up to n of BK, such that these be the sequences of partial sums for those two series. Then, by assumption, it says right here that this series is equal to A. But what does that mean? That means that the associated sequence of partial sums converges to A. Then, so by assumption, Sn converges to A. Similarly, Tn converges to B. So there's just unraveling the definitions of the assumptions. I want to show this is true. So I want to show something about that series. Well, to say something about that series, I need to say something about its sequence of partial sums. So that's what we'll do. Let's let Rn be the sequence of partial sums for this series. What does that mean? That means Rn is the sum from k equals 1 to n of AK plus BK. I will be happy if I can show that Rn converges to A plus B. So here's all we'll do. We'll use the fact that addition is commutative. So Rn is the sum from k equals 1 to n of AK plus BK. Certainly by the end of this series of lectures, everyone should be comfortable with summation notation, but for now I won't assume. Let's expand out that summation notation and just see what it is. So that's A1 plus B1 plus A2 plus B2 plus A3 plus B3 plus, and so on, all the way on up to AN plus BN. Now addition is commutative and associative, so maybe I'll add that word here, and associative. Associativity means I can erase all of those parentheses at no cost. Commutativity means that I can permute all of these variables to write them in a different order. So doing that, that is the same as A1 plus A2 plus A3 plus all the way on up until AN, plus B1 plus B2 plus plus BN. Oh, neat. So here I see a sequence of partial sums for AN. That has a name. Its name is Sn. Here I see a sequence of partial sums for Bn. That sequence of partial sums has a name. It's Tn. Or rather, I see the nth term in each of those sequences. So Rn is equal to Sn plus Tn. So let's just write that. I have space. So Rn equals Sn plus Tn. Now, by assumption, Sn converges to A, Tn converges to B. So by the additivity of limits, Rn, which is equal to Sn plus Tn, will converge to A plus B. Oh, hey, that's exactly what I wanted. I wanted to show that Rn converges to A plus B. There should be a period right here. So, what have we shown? Let's just summarize. Rn was the sequence of partial sums for the series given by the sum from k equals 1 to infinity ak plus bk. So the sequence of partial sums for that series converges to a plus b. So the series itself converges to a plus b, which is exactly what we wanted to show. Groovy. So, that was, if you like, a fairly light warm-up. As this bunch of lectures progresses, we're going to develop more sophisticated facts about series, and they'll all ultimately be facts which you'll remember from Calc 2. And maybe one of the first things that you remember from Calc 2 is the following intuitive fact. So if you add up a bunch of numbers, you have a series, you add up a bunch of numbers, and you get something finite, then not all of those numbers can be big. So let's prove that. Let's let AK be a sequence. Let's suppose that the sum of all of the AKs converges. Then the sequence AN converges to 0. The contrapositive of exactly that is if the sequence AN does not converge to 0, then the series diverges. And maybe I'll go ahead and point out this is not if and only if. And it's not claiming to be if and only if. In fact, the if and only if claim would just be false. So, let's prove this claim. The second claim is exactly the contraposition of the first claim, so we only need to prove the first. If we can prove the first, we'll know both are true. So, let's do that. So let's get the setup. Let's suppose that AK is a sequence. Let's suppose that the series of all of the AKs converges. I want to show that the limit of AN is equal to 0. So, there's the thing I want to show. So if that's what I want to show, I should start by considering any epsilon bigger than 0. And my assumption is something of the form this series converges. Saying that this series converges is really just something about the sequence of partial sums. Let's let Tn, doesn't matter what the name is, Tn is the thing that I chose when I wrote this, be the sum from k equals 0 up to n of ak. Let's let that be the sequence of partial sums associated to the sum from k equals 0 to infinity of ak. Oh, so you'll notice something already. This index starts at 0. Doesn't matter, you can replace it with 1 if you want. So, since the series itself converges, it must be that the sequence Tn converges. I don't know where it converges. It converges to whatever number the series converges to. One thing I do know, however, is that the sequence Tn is Cauchy. Right? Cauchy if and only if convergent. Well, so let's use that. So I'm just going to write down the definition of Cauchiness. So, from the definition of Cauchiness, since this epsilon is bigger than 0, there must exist some threshold value k, so that whenever m and n are bigger than k, absolute value of Tm minus Tn is less than epsilon. Well, okay. So, that's nice. This isn't what I want, though. I want to know something about an. But there's one thing that I do know about an. Let's point this out off to the side. If I take Tn plus 1 and subtract Tn, well, that's the sum of from k equals 0 to n plus 1 ak minus the sum from k equals 0 to n of ak. And you'll notice something immediately. All of these terms are also terms in this series. Sorry, sum. So that means we can cancel them. This is a sum of n plus 1 things, that's a sum of n things. But all of these n things are in there. So we can cancel a bunch of terms and see that this is exactly the same thing as just a sub n plus 1. Oh, neat. So that means that maybe instead of studying something that looks like Tm, something that looks like Tm and Tn, let's just study Tn plus 1 and Tn. Let's do that. So let's let big N be k plus 1. Let's consider any little n bigger than big N. So that means that both n and n plus 1 are greater than k. It follows then that, oh, these indexes are wrong, t sub n minus t sub, that epsilon is bigger than t sub n minus t sub n minus 1. Maybe by expanding out just a little bit, that's the same thing as the absolute value of the sum from k equals 0 up to n of ak minus the sum from k equals 0 up to n minus 1 of ak. Oh, but just like off to the side, a bunch of these terms will cancel. By canceling all the common terms, you'll be left with just absolute value of an. So that means an is less than epsilon. So what have we done? So we started out the proof by considering any epsilon bigger than 0. So we've proven something is true for every epsilon bigger than 0. We came up with a choice of big N, using the fact that Tn is Cauchy. We considered any little n bigger than big N, and we showed that, well, an is less than epsilon, but an is, of course, equal to absolute value of an minus 0. Oh, that means that an converges to 0, which is what the theorem claims. So, this is called the test for divergence because here's how you'll use it. If you want to show that a series diverges, one thing that you can test for, hopefully easily, is just look at the terms of the series. See if the terms of the series converge to 0. If they do, then the series might converge. No promises. It's not an if and only if. If the sequence does not converge to 0, then the series has no chance to converge. The series must diverge. Cool. So for most series that we'll study, it will be basically impossible to get an explicit formula for the limit. Indeed, a lot of series are used to construct interesting numbers or interesting functions. So we won't often care about saying exactly what the limit is. We'll just want to know that the limit exists. And here's basically the only series that I'll be able to compute on the nose. Fix a number p in the real number line. If the absolute value of p is less than 1, then the series, the sum from k equals 0 to infinity of p to the k, is 1 over 1 minus p. In all other cases, the series diverges. So let's try to prove that. So let's consider any p in the real number line. The bulk of the work comes from the following claim, and I'll skip it. It's the thing alluded to as the geometric sum formula. So for any number p, as long as p is not equal to 1, then the sum from k equals 0 up to n of p to the k is equal to 1 minus the next power of p divided by 1 minus p. And this is also noteworthy because generally it will be basically impossible to find explicit formulas for even finite sums. Here we have one. So let's suppose that we'll assume this claim. The proof of this claim is homework, I think. And there are lots of good proofs. You could, for instance, use induction. Whenever you have a formula for something that has an implicitly recursive definition, and there is a thing that has kind of a recursive definition, you should think about using induction. On the other hand, on the right-hand side of the thing to be proven is division. So you can move this 1 minus p to the other side and just try to expand out that. It's a finite sum, so you can use things you know about finite sums like the distributive law. Okay, but that's enough stalling. So let's use that claim and prove the theorem. So let's assume that absolute value of p is less than 1. In particular, then, p itself is not equal to 1. Maybe I'll write down the thing that we want to show in this case. In this case, we want to show that the sum k equals 0 to infinity of p to the k is equal to 1 over 1 minus p. That's what we want to show. Well, let's try to do it. So by claim 2.9.5, the sequence of partial sums is given by Tn equal to the sum from k equals 0 to n of p to the k. The formula is right here. Let's use it. Is equal to 1 minus, sorry, I want this in black, 1 minus p to the n plus 1 all over 1 minus p. And I want to take the limit of this thing as n goes to infinity. So let's just think about what you would need to do to take this limit. So that's a constant, that's a constant, that's a constant. There's the only n I see. As n goes to infinity, p to the n plus 1, well, that's multiplying a bunch of times by a number that's less than 1. So that limit will be 0. So the limit of this whole thing, by limit laws, will be 1 minus 0 over 1 minus p. That's all I need. So since absolute value of p is less than 1, the limit of p to the n plus 1 is equal to 0. Thus, the limit of Tn is equal to the limit of 1 minus p to the n plus 1 over 1 minus p is equal to 1 minus 0 over 1 minus p by limit laws is equal to 1 over 1 minus p. Oh, neat. So that means that the sequence of partial sums converges to 1 minus p. The sequence of partial sums converges to 1 minus p. So that means that the series itself converges to 1 over 1 minus p. And in fact, the proof in the divergence case is super similar. When p is bigger than 1 in absolute value, well, this bit will go off to infinity. So now you can use limit laws to conclude that the whole thing will diverge to plus or minus infinity, or neither, maybe. Cool. So, there's the one type of series that is possible to compute. Here's another one. Telescoping series have limits that you can compute. And let's state that. So this is sometimes called the telescoping series test. Let's let Cn be a sequence which converges to some number c. Let's let Ak be the sequence given by Ak equal to Ck minus Ck plus 1. Then, the sum from k equals 1 to infinity of Ak converges to C1 minus that limiting value c. Alright, so proceeding, let's do it. So let's let Cn be a sequence which converges to some number c. Let's let An be given by the thing that we say it's given by, the difference between two consecutive terms of the sequence Cn. Let's let big Sn be the sequence of partial sums for the series of AKs. Then, well, let's just expand everything out. If we want to show that the series converges to C1 minus C, I need to show that the sequence of partial sums converges to C1 minus C. Let's just try to understand what the sequence of partial sums is. So, let's write down what Sn is. So, Sn is the sum from k equals 1 to infinity of Ak, but I know what Ak is. That's the same as the sum from k equals 1 to infinity, and I'm going to be very careful with my subscripts because I've already had to re-record this once because of screwing up the subscripts. Ck minus Ck plus 1. And I can expand this out. Okay, so I guess these are kind of out of order. So I can expand this now by the definition of partial sums, and because AK is equal to CK minus CK plus 1. There, that's been used, what's used in that step. Next, I think that I want to expand everything out. So let's do that. Let's see, by expanding, let's see what we get. So that will be, so what's the term when k is equal to 1? I'll see C1 minus C2. There's the k equals 1 term. Plus, Chris. Those should be n's. Next, the k equals 2 term. That'll be C2 minus C3. And I want to keep on going. Let's write one more term before we put the dot, dot, dot. Plus C3 minus C4. Right here is the k equals 3 term. Carrying on. We'll stop when we make it to the nth term, Cn minus Cn plus 1. So there's the term when k is equal to n. So let's just look at that and see what we see. So certainly the parentheses don't matter because addition is associative. I could reorder things because addition is commutative, but I think I don't want to because I see some things that cancel. C2 minus negative C2 plus C2, those cancel. Negative C3 plus C3, those cancel. Negative C4 in this next term, which isn't written, plus C4, those will cancel. The last term that is going to show up right here will be Cn minus 1 minus Cn. So this Cn will cancel with that term. So I can cancel a whole mess of terms, and I'll wind up with C1 minus Cn plus 1. Oh, nice. So I can just use limit laws now. I have an explicit formula for Sn. The explicit formula isn't complicated, so I can probably just take its limit. So the limit of Sn will be exactly the same as the limit of C1 minus Cn plus 1, because Sn is the same as C1 minus Cn plus 1. So I can just replace this Sn with C1 minus Cn plus 1. This limit is now super easy to take. This is a constant. There's a sequence. This will be exactly equal to C1 minus the limit as n goes to infinity of Cn plus 1. But I know what Cn converges to, and Cn plus 1 is just a subsequence of that. So that'll be the same thing as C1 minus the limit of Cn, also known as C1 minus big C. So the sequence of partial sums converges to C1 minus C, so the series converges to C1 minus C. Cool. So carrying on, let's use this to do a quick computation as an application. Let's let AK be the sequence given by 1 over k times k plus 1, which I assert is equal to 1 over k minus 1 over k plus 1. You can go ahead and check that by doing some algebra if you want to. Go ahead and pause the video if you want to do that. Then this series converges. In fact, we'll see where it converges, but the statement of the corollary doesn't care where it converges. The proof of this claim will be an immediate consequence of the proposition above, and the hint that that's true is that's what the word corollary means, right? So let's try to do it. Let's try to prove this corollary. Well, carrying on, let's try to do it by setting up a telescoping series argument. So read this. So if Cn is a sequence which converges to some number c, and ak is always equal to ak minus ak plus 1, then the series associated with ak converges. So I need to find a sequence Cn that achieves this equality for that sequence. And, well, this line kind of tells you what you should use. Let's let Cn be exactly 1 over n. Then that sequence converges to 0, which I've called big C, because in the telescoping series argument it's called big C. A thing which I will need to be true is I will need an to be the same thing as cn minus cn plus 1. So let's do that. Let's check that. That is actually the case. So you'll notice an inconsistency then. I said cn minus cn plus 1. I've written here cn plus 1 minus cn. That'll be corrected in the actual version that you will see. So let's compute cn minus cn plus 1. So by the definition of all of these things, cn is 1 over n minus 1 over n plus 1 is equal to, get a common denominator, n plus 1 minus n all over n times n plus 1. Well, that's 1 over n times n plus 1, which is exactly an. So, what have I done now? I have shown the existence of a sequence cn, which converges to 0, and which satisfies that cn minus cn plus 1 is equal to an. So let's scroll up a little bit. I said scroll up a little bit. I found a sequence cn which converges to some number c, namely c equals 0 in this case. ak is a sequence given by ck minus ck plus 1. Then I conclude that the sum of all from k equals 1 to infinity of ak is exactly this. Oh, neat. So that's exactly the situation I'm in. So I conclude that the series of all of these ak's is the same as C1 minus big C. That stall there was to make sure I wasn't about to make a sign error, because, as I said, this is like the second time I've recorded this because of stupid sign errors. What is C1? Well, it's 1 minus 0, which is 1. But I don't actually care about that. If you notice in the corollary, I just say that the series converges. I don't say where it converges. In particular, then, the series of all of these ak's converge to 1, but I don't care that it converges to 1. Cool. So I'll stop there. Yeah, I'll stop there. I hope you guys are enjoying at least a little bit these videos. I'll be in touch.